Hi, welcome to Supervised Learning with scikit-learn. Here you get a chance to grow your machine learning skills with scikit-learn and discover how to use this popular Python library to train models using labeled data. In this course, you'll learn how to make powerful predictions, such as whether a customer will churn from your business, whether an individual has diabetes, and even how to classify the genre of a song. Using real-world datasets, you'll find out how to build predictive models, tune their parameters, and determine how well they will perform with unseen data. This course consists of 4 chapters, which are classification, regression, fine-tuning your model, and lastly, preprocessing and pipelines. In this video, we'll be covering Chapter 2 of Supervised Learning with scikit-learn, regression. In this chapter, you will be introduced to regression, and build models to predict sales values using a dataset on advertising expenditure. You will learn about the mechanics of linear regression and common performance metrics such as R-squared and root mean squared error. You will perform k-fold cross-validation, and apply regularization to regression models to reduce the risk of overfitting. Let's begin with introduction to regression. In regression tasks, the target variable typically has continuous values, such as a country's GDP, or the price of a house. To conceptualize regression problems, let's use a dataset containing women's health data to predict blood glucose levels. It contains features including number of pregnancies, triceps skin fold measurements, insulin levels, body mass index, known as BMI, age in years, and diabetes status, with 1 indicating a diagnosis, and 0 representing the absence of a diagnosis. Links to web pages and datasets used in the upcoming slides are given in the description of this video. To get started, first download the latest Python from the official website you can see in this screenshot. Next, you need an integrated development environment, IDE. I would recommend using PyCharm Community Edition, which is a Python IDE, but you can also use any other tool of your choice which supports Python development. After downloading PyCharm, install it and create a new project with configurations you can see in this screenshot. For next couple of practicals, you need 3 libraries, NumPy, Matplotlib and Pandas, which are given in the screenshots you can view. Just copy the names of these libraries and install them using pip. You can view the screenshot how to install the 3 libraries before you can import them in your next code practice. Recall that scikit-learn requires features and target values in distinct variables. To use all of the features in our dataset, we drop our target, blood glucose levels, and store the values attribute as feature. For target, we take the target column's values attribute. We can print the type for feature and target to confirm they are now both NumPy arrays. To start, let's try to predict blood glucose levels from a single feature, body mass index. To do this, we slice out the BMI column of the feature variable, which is the 4th column, assigning it to the BMI variable. Now we have both target and feature variables, but we see that they are both one-dimensional arrays. This is fine for the target, but our features must be formatted as a 2-dimensional array to be accepted by scikit-learn. To convert the shape of the feature, we apply numpys.reshape method, passing -1 followed by 1. Printing the shape again shows the feature is now the correct shape for our model. Now, let's plot blood glucose levels as a function of body mass index. We import matplotlib.pyplot as plt, then pass BMI and target to plt.scatter. We'll also label our axes using the x-label and y-label methods. We can see that, generally, as body mass index increases, blood glucose levels also tend to increase. For working with scikit-learn, you will have to install the scikit-learn library from the Python package index website you can see in the screenshot. Just copy the pip command and execute it in the terminal window inside IDE you can see in the screenshot. It's time to fit a regression model to our data. We're going to use a model called linear regression, which fits a straight line to our data. We will explain the mechanics of linear regression in the next video, but first, let's see how to fit it and plot predictions. We import linear regression from sklearn.linear_model, and instantiate our regression model. As we are modeling the relationship between the feature, body mass index, and the target, blood glucose levels, rather than predicting target values for new observations, we fit the model to all of our feature observations. We do this by calling reg.fit and passing in the feature data and the target variable, the same as we did for classification problems. After this, we can create the predictions variable by calling reg.predict and passing in our features. As we are predicting the target values of the features used to train the model, this gives us a line of best fit for our data. We produce our scatter plot again, and then call plt.plot to produce a line plot, passing our features, followed by our predictions. The black line represents the linear regression model's fit of blood glucose values against body mass index, which appears to have a weak to moderate positive correlation. So, now we are going to learn how does linear regression work. We want to fit a line to the data, and in 2 dimensions this takes the form of y equals ax plus b. Using a single feature is known as simple linear regression, where y is the target, x is the feature, and a and b are the model parameters that we want to learn. A and b are also called the model coefficients, or the slope and intercept, respectively. So how do we accurately choose values for a and b? We can define an error function for any given line and then choose the line that minimizes this function. Error functions are also called loss or cost functions. Let's visualize a loss function using this scatter plot. We want the line to be as close to the observations as possible. Therefore, we want to minimize the vertical distance between the fit and the data. So for each observation, we calculate the vertical distance between it and the line. This distance is called a residual. We could try to minimize the sum of the residuals, but then each positive residual would cancel out each negative residual. To avoid this, we square the residuals. By adding all the squared residuals, we calculate the residual sum of squares, or RSS. This type of linear regression is called ordinary least squares, or OLS, where we aim to minimize the RSS. When we have 2 features, x1 and x2, and 1 target, y, a line takes the form y equals a1x1 plus a2x2 plus b. So to fit a linear regression model we specify 3 variables, a1, a2, and the intercept, b. When adding more features, it is known as multiple linear regression. Fitting a multiple linear regression model means specifying a coefficient, a n, for n number of features, and b. For multiple linear regression models, scikit-learn expects 1 variable each for feature and target values. Let's perform linear regression to predict blood glucose levels using all of the features from the diabetes dataset. We import linear regression from scikit-learn.linear model. Then we split the data into training and test sets, instantiate the model, fit it on the training set, and predict on the test set. Note that linear regression in scikit-learn performs OLS under the hood. The default metric for linear regression is r squared, which quantifies the amount of variance in the target variable that is explained by the features. Values can range from 0 to 1, with 1 meaning the features completely explain the target's variance. Here are 2 plots visualizing high and low r squared, respectively. To compute r squared, we call the models.score method, passing the test features and targets. Here the features only explain about 28% of blood glucose level variance. Another way to assess a regression model's performance is to take the mean of the residual sum of squares. This is known as the mean squared error, or MSE. MSE is measured in units of our target variable, squared. For example, if a model is predicting a dollar value, MSE will be in dollars squared. To convert to dollars, we can take the square root, known as the root mean squared error, or RMSE. To calculate RMSE, we import mean squared error from sklearn.metrics, then call mean squared error. We pass target test and predictions, and set squared equal to false, which returns the square root of the MSE. The model has an average error for blood glucose levels of around 26 mg per deciliter. Hopefully we are now feeling familiar with train test split and computing model performance metrics on our test set. But, there is a potential pitfall of this process. If we're computing r squared on our test set, the r squared returned is dependent on the way that we split up the data. The data points in the test set may have some peculiarities that mean the r squared computed on it is not representative of the model's ability to generalize to unseen data. To combat this dependence on what is essentially a random split, we use a technique called cross-validation. We begin by splitting the dataset into 5 groups or folds. Then we set aside the first fold as a test set, fit our model on the remaining 4 folds, predict on our test set, and compute the metric of interest, such as r squared. Next, we set aside the second fold as our test set, fit on the remaining data, predict on the test set, and compute the metric of interest. Then similarly with the third fold, the fourth fold, and the fifth fold. As a result we get 5 values of r squared, from which we can compute statistics of interest, such as the mean, median, and 95% confidence intervals. As we split the dataset into 5 folds, we call this process 5-fold cross-validation. If we use 10 folds, it is called 10-fold cross-validation. More generally, if we use k-folds, it is called k-fold cross-validation or k-fold CV. There is, however, a trade-off. Using more folds is more computationally expensive. This is because we are fitting and predicting more times. To perform k-fold cross-validation in scikit-learn, we import cross-val score from sklearn.model selection. We also import k-fold, which allows us to set a seed and shuffle our data, making our results repeatable downstream. We first call k-fold. The n-splits argument has a default of 5, but in this case we assign 6, allowing us to use 6 folds from our dataset for cross-validation. We also set shuffle to true, which shuffles our dataset before splitting into folds. We also assign a seed to the random state keyword argument, ensuring our data would be split in the same way if we repeat the process, making the results repeatable downstream. We save this as the variable kf. As usual, we instantiate our model, in this case, linear regression. We then call cross-val score, passing the model, the feature data, and the target data as the first 3 positional arguments. We also specify the number of folds by setting the keyword argument CV equal to our kf variable. This returns an array of cross-validation scores, which we assign to CV score. The length of the array is the number of folds utilized. Note that the score reported is r squared, as this is the default score for linear regression. We can now print the scores. This returns 6 results ranging from 0.23 to approximately 0.4. We can calculate the mean score using np.mean, and the standard deviation using np.std. Additionally, we can calculate the 95% confidence interval using the np.quantile function, passing our results followed by a list containing the upper and lower limits of our interval as decimals. Now let's explore regularization and regression, a technique used to avoid overfitting. Recall that fitting a linear regression model minimizes a loss function to choose a coefficient, a, for each feature, and the intercept, b. If we allow these coefficients to be very large, we can get overfitting. Therefore, it is common practice to alter the loss function so that it penalizes large coefficients. This is called regularization. The first type of regularized regression that we'll look at is called RIG. With RIG, we use the ordinary least squares loss function plus the squared value of each coefficient, multiplied by a constant, alpha. So, when minimizing the loss function, models are penalized for coefficients with large positive or negative values. When using RIG, we need to choose the alpha value in order to fit and predict. Essentially, we can select the alpha for which our model performs best. Picking alpha for RIG is similar to picking k and knn. Alpha in RIG is known as a hyperparameter, which is a variable used for selecting a model's parameters. Alpha controls model complexity. When alpha equals 0, we are performing OLS, where large coefficients are not penalized and overfitting may occur. A high alpha means that large coefficients are significantly penalized, which can lead to underfitting. To perform RIG regression in scikit-learn, we import RIG from sklearn.linear model. To highlight the impact of different alpha values, we create an empty list for our scores, then loop through a list of different alpha values. Inside the for loop we instantiate RIG, setting the alpha keyword argument equal to the iterator, also called alpha. We fit on the training data, and predict on the test data. We save the models our squared value to the scores list. Finally, outside of the loop, we print the scores for the models with 5 different alpha values. We see performance gets worse as alpha increases. There is another type of regularized regression called lasso, where our loss function is the OLS loss function plus the absolute value of each coefficient multiplied by some constant, alpha. To use lasso we import it from sklearn.linear model. The actual method for performing lasso regression in scikit-learn mirrors RIG regression, as we can see here. Performance drops substantially as alpha goes over 20. Lasso regression can actually be used to assess feature importance. This is because it tends to shrink the coefficients of less important features to 0. The features whose coefficients are not shrunk to 0 are selected by the lasso algorithm. Let's check this out in practice. We import lasso. Next, we create our feature and target arrays, and use the datasets.columns attribute to access the feature names and store as the variable names. As we are calculating feature importance we use the entire dataset, rather than splitting it. We then instantiate lasso, setting alpha to 0.1. We fit the model to the data and extract the coefficients using the .coef_ attribute, storing as lasso_coef. We then plot the coefficients for each feature. We can see that the most important predictor for our target variable, blood glucose levels, is the binary value for whether an individual has diabetes or not. This is not surprising, but is a great sanity check. This type of feature selection is very important because it allows us to communicate results to non-technical audiences. It is also useful for identifying which factors are important predictors for various physical phenomena. Thanks for watching. In the next video of the playlist, we'll learn to evaluate trained models. We'll be introduced to several metrics along with a visualization technique for analyzing classification model performance using scikit-learn. We will also learn how to optimize classification and regression models through the use of hyperparameter tuning. Feel free to ask any questions in the comments section and we'll be pleased to answer those. Like and subscribe to stay updated about our upcoming videos about artificial intelligence. See you in the next video.